Okay, so now that we've defined work and energy and how they are related to each other, we are going to apply the equations that we found to see how they would work in a real world setting. So I've chosen this roller coaster problem. So we want to determine the required height of the roller coaster, h, so that when it is essentially at rest at the top of the hill, point A, it will reach a speed of 100 kilometers per hour at point B at the bottom. What should be the radius? What should be the radius of curvature rho so that the cart does not experience a normal force greater than 39.24 times the mass newtons? So first thing we want to do, I've kind of already started a little bit, but we want to draw a force diagram, force body diagram on the cart. So here we have the force due to gravity, mass times the acceleration due to gravity, and we have the normal force from the path. And then the second thing we want to do is we want to go through the equation, or through the problem, equation, and find the variables that we already know and figure out what we want to solve for. So the cart is essentially at rest at the top of the hill at point A, so VA equals 0 meters per second. And we want to find the required height so that when it is at point B, the cart is going 100 kilometers an hour. So VB equals 100 kilometers an hour. And I've gone ahead and converted that to meters per second, because here we have meters per second, doesn't really matter, but here the acceleration due to gravity is typically in meters per second squared. So we need units to be consistent. With that, we can apply our work and energy equations. We have velocities, we have forces. Let's see how they work. So we know that the work equals the change in kinetic energy. We have the initial and final velocities, so we can plug them into this equation. We have the integral of the force due to gravity times dH, and you'll notice that while it doesn't look like the force is along the path, the force downward is in line with what we are trying to find, dH. So they're both only in the y direction. So that's why there's no angle that we have to worry about. So we want mg times dH, integral with respect to dH, equals the change in kinetic energy. So 1/2 mvb squared minus 1/2 mva squared. And the bounds on this integral would be from, we'll call this h1 and this one h0. So it'll start from h1 to 0, because it starts at h1 and goes to 0. Or I guess we'll just call it h. H, and then it goes to 0. Okay, so what we want to do is we want to solve for h. So let's go ahead and do that. Let's see, we have mg times, mg times 0 minus h equals 1/2, excuse me, mv squared minus 1. Okay, so next thing we see here, that the mass, if we can divide it out, so the problem does not, the mass doesn't affect the problem at all. And then we can divide g over and essentially solve for h. So we'll have negative height equals 1/2 the m's will all cancel, so I'll have negative b squared minus 1/2 the a squared over g. And we can just get rid of this negative by bringing that over 2. So we'll have h equals, we'll just say 1/2 times a squared minus b squared, because if we switch the minus signs, over g. And then plugging in values, we will get 1/2 times 0 squared minus 100 squared. Sorry, not 100. 27.8 meters per second. 27.8 meters per second squared. Over negative 9.81 meters per second squared. Yeah, and then all we have to do is solve for h. So h equals, let's see, h should equal 1/2 of, that would equal 39.3 meters. Now for the radius of curvature. So let's see. So we know at point B, the sum of all the forces equals the gravity, force due to gravity. Sorry, backwards. Should be the normal force minus the force due to gravity. And the sum of the forces also equals MA. And MA can be substituted in with mv squared over rho. And then using these two, we find that n minus mg equals mv squared over rho. And the value for n, the max value for n, is 39.2 times m. So we can plug that in, 39.24 m newtons minus mg equals mv squared rho. So again, we see the mass will all divide out. So we have 39.24 n minus g equals v squared over rho. Multiplying rho over and dividing by 32 minus this whole term here, we get rho equals v squared over 39.24 minus g, 2.4 n minus g. And that would be the velocity at B. So that would be velocity B, velocity B, velocity B, B, B. So rho equals 27.8 meters per second squared over 39.24 newtons minus, no, newtons actually, 32.4 minus 9.81. Rho should equal 26.3 meters. There we have it. Work and energy.